back from break. So this was the reaction that we were looking at. We were looking at the formation of deuterium, and we had gotten this far. And so I'm taking a proton and a neutron, combining it to form a deuterium nucleus, and by doing a Q calculation, we converted everything so that everything is a neutral isotope. Looked those up in Appendix F. Appendix F is your friend. And did the Q calculation and found out that we get 2.2 MeV of energy released in the reaction. Now, here is a series of nuclear fusion reactions, and the reactions that we show here are some of the prominent nuclear fusion reactions that are going on inside stars. So the sun is kind of in the prime of its life, I guess. We expect that the sun will undergo nuclear fusion reactions. It will continue to shine for maybe 10 billion years. Our best estimates as to when the solar system formed about 5 billion years ago, and so that suggests that, you know, the sun is about halfway through its lifetime in terms of nuclear fusion reactions. And the reactions that are running on the sun, now let's think about what this notation really means. Hydrogen 1 is just a proton. So this is saying proton plus proton produces deuterium. Now that's different from the reaction we just looked at. This is not a proton and a neutron, but it's a proton and a proton. It's two protons converting into deuterium. And that is, that's a more difficult reaction to run, because in the process, one of the protons has to convert into a neutron. This is like beta plus decay, where a proton turns into a neutron along the way. Now, there's not a lot of energy margin to work with. Notice that with this reaction, the Q values, these are all Q values, is not much. There's barely enough mass in those two protons to produce deuterium. But here it is. Here are the protons producing a neutron and a proton here. Now in the process, we're going to get an anti-electron. That's kind of interesting too, that when stars are running these nuclear fusion reactions, it actually generates antimatter. Specifically, it generates anti-electrons. Every time a neutron gets formed from a proton, an anti-electron is produced at the same time. Now, what can also happen is once the deuterium gets produced, that can react with other protons that are around to form a helium-3 nucleus along with high-energy photons. And then once you get these helium-3 nuclei inside the star, this is in the core of the star. So these reactions, remember that there's a, what the textbook is calling a Coulomb barrier. There is an electric force repulsion taking place between all of these nuclei. Protons repel each other. Deuterium nuclei and protons repel. The helium-3 nuclei repel each other. They've got to be moving at high speed. And that means we have to be at really high temperatures. So when a star first forms, there's a lot of energy released from gravitational collapse. The formation of the star from a large, really spread out region of hydrogen and helium gas releases a lot of energy, just as dropping something over and over releases a lot of gravitational potential energy. So these are at really high temperature, meaning that they're moving really fast, fast enough to overcome the repulsive forces. But the temperatures are only high enough in the core region of the star. These are not reactions happening at the surface. When we look at the sun and we see the light coming off the surface, that light is not coming directly from nuclear fusion. Fusion reactions are deep, deep inside the core of the star. All right, so here's a couple of helium-3s. They can react and form a helium-4 in addition to a couple of protons. Now, when you add all these together, what's happening is, you know, some of the protons are being recycled, but the general trend is to take some number of protons and form a helium-4 nucleus along with some anti-electrons, some positrons, and some neutrinos. So what movie was that? It's been a while now. It's maybe 10, 15, 20 years ago. There was some movie, maybe it was called The Core. No. Where they determined that the sun's fusion reactions were stopping. And they determined that because they were monitoring the neutrinos. Now, neutrinos are formed in the core of the sun in these nuclear fusion reactions, but they don't react with anything. So they just fly right out of the sun, so we can get immediate information about what's going on in the core of the sun by monitoring the number of neutrons being produced. And anyway, in the movie, the scientists had watched this steady drop of neutrinos and realized that the fusion reactions on, I think that was the story. Anyway, so these are the kind of reactions that are going on. Now look at the Q values. That first reaction, you know, barely works, but the others are releasing a lot of energy. Okay, so what I did was I outlined all these. I wrote down, this has to happen twice, and this has to happen twice, and this has to happen once. And the helium-3 is being recycled, and the deuterium is being recycled, so that the net reaction is 1, 2, 3, 4 hydrogen 1s form helium-4 plus 2 anti-electrons plus 2 neutrinos. So that means I can take 2 of these Q values, 2 of these, 1 of these. Every time we run that reaction, all the fusion reactions are going to give us 24.70 MeV. That's the amount of energy that's released. That is a lot of energy from just 4 protons. Basically, we're starting with 4 protons. They're being converted into a helium-4 nucleus. Along the way, 2 of the protons become neutrons, and that stabilizes them. Neutrons, I think we've talked about this before, neutrons aren't stable. Neutrons have a half-life of like 15 minutes, and then they decay into protons and electrons and neutrinos. But once the neutrons are part of a nucleus, then the neutrons are no longer free to decay unless it's undergoing beta-minus decay. So in a stable nucleus, there's not enough mass margin to work with, and the neutrons are stuck. They become stable. So all the neutrons that you're made out of and all the neutrons that the planet's made out of came from these reactions. So it came from the reaction, well, this reaction right here, where one of the protons turned into the neutron, it got built into a stable nucleus, and then the neutrons are stuck. They remain neutrons, they don't decay. Let's see, adding all these together, we got 24.7. Now there's a bonus here, and that is along the way we created some anti-electrons. And so we can take the anti-electrons and react them with electrons. There's electrons going on here. You know, if you go to the core of the sun, there are no atoms. There are just nuclei and electrons. It's plasma at high enough temperatures. The electrons don't stay attached to a nucleus. So there's a bunch of free electrons running all over the place, and there's a bunch of these protons, those are just protons, and deuterium nuclei and helium nuclei. These nuclei and these electrons are just zipping all over at high speed. And so when we generate a couple of anti-electrons, they react with a couple of the electrons, form a bunch of high-energy photons. Now, I know sometimes students say, well, if you take matter and antimatter, doesn't it form pure energy? And not sure what pure energy means. So when particles react, other particles come out of the reaction. And when we react an electron with an anti-electron, that will form a pair of high-energy photons. So this matter-antimatter reaction produces high-energy photons. Now we can calculate the Q. The Q value here is, hey, it's the entire mass, right? Because there's no mass left. That entire mass has been converted into kinetic energy. And I'm sure that's where the statement of pure energy comes from. But in any case, whatever mass was here, 100% of it has been converted into the kinetic energy of those photons. So that gives us a Q of 2.04. Adding those together, one round of, what do we got now? If I take 4 of these, there should be a 4 here. If I take 4 of these hydrogens, hydrogen 1s, that's like saying 4 protons and 4 electrons, and we run through these reactions, we are going to generate 26.74 MeV of energy. That's how much energy gets released, including, most of it's coming from fusion, but 8% or something is coming, is that right? Is coming from matter-antimatter reactions. Here is the net reaction right there. That's the one I wanted. And when we do a ratio of energy that we get out compared with the mass we put in, it's 1 part in 139. So very roughly, we're getting very close to converting 1% of the mass into energy. All right, and this is that reaction. There we go. So this is the net result of the fusion reactions for hydrogen 1s. Now these are really protons and these are helium nuclei. I should have put plus here and plus here so we could charge balance. Again, that would be 4 pluses here, 2 pluses here, and 2 pluses here, charge balanced. All right, and then this hasn't included. Okay, here's some more fusion reactions. So stars that are a little heavier than the sun are able to generate amounts of carbon and nitrogen even during their regular, the main sequence part of their lifetime. And so these are other fusion reactions that go on. Once you get a little bit of carbon generated and nitrogen and oxygen, you can cycle through this series of reactions. It's called the HNO cycle, and the net reaction, surprisingly, if you run through there and cross out, like here we generated nitrogen 13, but we used it up here. Here we generated nitrogen 14, and we used it up over here. So once you cross everything out, it turns out it's the same effect. The net effect is 4 hydrogens forming a helium-4. Okay, what would be the heaviest element likely to be produced? Now, the heaviest element that can be produced and still release energy would be iron. So the heaviest stars, and we'll see this in the final chapter of the course when we look at astrophysics, but the heaviest stars are able to fuse elements all the way up to and including iron, and a little bit beyond. But when they start generating elements beyond iron, that actually requires energy. So it's not releasing any energy anymore. So once you've reached iron, then the stars really don't have a way to generate more energy from fusion processes. Now here are some reactions, fusion reactions, that researchers have pointed towards as a possibility for a fusion power plant. What if we were to generate electricity using a fusion power plant? And notice that these reactions, some of them are pretty energetic. None of them involve converting protons to neutrons. So we've left that reaction out. That's a more difficult one to replicate in a power plant in conditions here on planet Earth. But there are other fusion reactions that we can reliably, we have run all of these reactions in labs. Now it's saying that the common fuels here are deuterium, which is common enough, but it's also saying tritium. Tritium has to be generated. We have to run reactions to generate the tritium, but it can be done. So we can, I think you can purchase canisters of deuterium. It's not cheap, but it's not super expensive, right? It's a manageable cost. So here we go. It's a nuclear fusion power plant. We're going to run this reaction. I don't know why we chose this one, but we did. Is this the one they asked us to choose? Nope. Okay, anyway, let's look at a power plant that's nuclear fusion. We'll take a deuterium plus a tritium and make helium, and we'll release a neutron. I got all their masses. The Q calculations should be familiar at this point. It says, oh, that's why we went with this one. Whoa, this one releases a lot of energy. Of course, we got to come up with a tritium to run this. So then that's not going to be trivial. Deuterium exists in nature. Deuterium is stable. Tritium is radioactive, and it only has a half-life of like 10 years, 10 or 12 years, something like that. And so tritium would have to be produced, but let's go ahead. This is the Q value. It says that if we do this energy to mass fraction, it says when we run this reaction, 1 part out of 266 of the mass is being converted to energy. So if we take that very same 1,000 megawatt power plant that we talked about before, 33% efficiency, that is going to require 9.6, we're going to have to generate this much thermal energy. So I'm borrowing this number from a previous example and putting in the Q value for this deuterium-tritium reaction says that we would need to run this reaction 3 times 10 to the 28th times. So sometimes in the reactions it's just easier to go in, get the total amount of energy we need, and from that calculating how many times do we have to run that reaction to create that much energy. And that's what I've done here. And so for the deuterium, I'm going to need that many deuteriums, and I'm going to need that many tritiums. And so it says I only need 114 kilograms. Now, how much was the uranium-235 in our power plant? That was like 1,300 kilograms of uranium. Well, look, I only need a couple of 100 kilograms of deuterium. Well, a little over 100 grams of deuterium and a little less than 200 kilograms of tritium. And we can generate the same amount of energy. Okay. So the nuclear fusion power plants are a real, could potentially be a real source of a lot of energy with a relatively low amount of fuel that we have to put in. The technology is very difficult. When I was a kid, which you guys can guess was a while ago, and even in elementary school, I don't know, 4th, 5th, 6th grade, I was reading books on nuclear power. And at that time, I would read that nuclear fusion plants were just around the corner. We were just on the verge of generating all of our electricity through nuclear fusion. And here we are many, many, many years later, and it's kind of the same situation. Researchers are still trying to figure out some kind of a reactor where they can reliably and safely run these nuclear fusion reactions and generate electricity. Let's take a look at the temperatures that would be needed. So this is one of the issues. One of the technological issues is in order to get deuterium and tritium to react with each other, what temperature would we need? Now, we've done these potential energy barrier calculations before. So this is KQ1, Q2 over R, and that's the electromagnetic force constant, times Z1, these are the atomic numbers. Now, both tritium and deuterium have an atomic number of 1, but their mass numbers are different. They have different numbers of neutrons. And then the R0 value, the kind of scaling factor for the size of the nucleus, is given by 1.20 femtometers. So this is the formula we've used before, and that's calculating, well, the potential energy. It says that the potential energy barrier is 0.444 MeV. So what we would like to have is that the deuterium and the tritium inside the combustion reactor chamber for our nuclear power plant would have kinetic energies of that magnitude. So if I've got the deuterium and the tritium zipping around as a plasma inside a reaction chamber of, this is the energy we would need to get. We can go back to chapter, I guess it was chapter 18, when we said kinetic energy is related to temperature. The little k here is Boltzmann's constant. Now it's been a while, but if you remember, we've used little k for everything. How many things have we used little k for through the 2 semesters? Way too many. So this is Boltzmann's constant. And in MEV, it looks like this. Putting the numbers into that formula says that all we need is a reaction chamber where the temperatures are 3.4 billion kelvins. Okay, so, that doesn't look likely to happen. So that's very difficult to get the deuterium and the tritium up to these speeds, to these energies. Now, again, it's a reminder that even though fusion power plant technology has not been developed, we have learned how to use nuclear fusion as a weapon. So pretty much all of the nuclear weapons in so-called advanced countries now are based on a fission reaction igniting a fusion reaction. So the high temperatures generated from a fission reaction allow the fusion reactions to kick in. Yeah, and then they talk about power plants here. So let's take a look and see. Here's an example. A tokamak is what it's called. It's kind of a torus, it's kind of a donut-shaped vessel. So it's a reaction vessel. It's kind of donut-shaped. And what the donut shape allows for is the formation of magnetic fields in the toroid shape. We actually looked at some of these examples, not of a reaction vessel, but as magnetic fields in toroids, back in chapter 28, maybe? Anyway, you can set up these magnetic fields, and that will help to contain the high energy particles. And then what we can do is we can use, we can just broadcast radio energy photons into the chamber, just flood it with a lot of energy, and bring the deuterium and the tritium up to really high speed. And then the idea is to use this geometry along with some magnetic fields so that if the deuterium or tritium begins to head towards the materials of the chamber, that it's deflected away. But so far, we don't have a successful, ooh, look, there's the person. The person's really small. I just realized that. But research is continuing into nuclear fusion power plants. Of course, the real concern is that some technology might come along that enables the easy development, the too easy development of nuclear fusion reactions. All right, let's see. Final topic in the chapter, chapter 42. So we're going to wrap stuff up with nuclear, all of our nuclear physics stuff here. So we've talked about different types of radioactive decay. We've talked about alpha, beta, gammas. We've talked about X-rays in previous chapters. Any of these high energy particles are referred to as ionizing radiation because they ionize material. What does that even mean? It means that the electrons are taken out of their chemical bonds. So when something is ionizing, what it's doing is it's breaking the chemical bonds. It's removing electrons, and it's changing the actual makeup of the materials. Molecules are being taken apart. And so, as we had mentioned, if we run, if we have alpha decay going on, if we have some kind of a radioactive decay process, like uranium. Uranium undergoes alpha decay. That produces helium nuclei. When the helium nuclei are going fast, that's an example of ionizing radiation. But when the helium nuclei slow down, that's called helium. And we mine for helium deep in the earth. Where is that helium coming from? It's radioactive decay. It's alpha decay of materials like uranium inside the planet, and every time alpha decay occurs, a nucleus of helium is formed. And so that's where our sources of helium are coming from. You may have read that helium is possibly running out. Well, if helium runs out, we're going to have to be patient to let a lot of radioactive decay regenerate more helium within the planet. All right, let's take a look at what we need to know with this. I'm a little nervous about this. Okay, first of all, let's get a couple things out of the way in calculating this. The units that get used for this, I always feel like are a little confusing, at least for myself. It says that the rate of decay is measured in what are called curies. Okay, and the symbol for a curie is a CI, which is hard to remember for me. 1 curie is 3.7 times 10 to the 10 decays per second. Why don't they just say that? Why don't they just say it's a decay rate of 3.7 10 to the 10 decays per second? I'm not sure why we have invented these other units. Anyway, we need to know that unit in order to solve this problem, because what they're saying is we have a sample of a radioactive isotope of phosphorus. It's phosphorus 32, and we're going to use that in some kind of an experiment. We're actually going to use it in bacteria. We're going to inject the bacteria with some radioactive phosphorus 32 that I'm going to guess, this is a wild guess, but I'm going to guess that phosphorus is incorporated into some DNA. So in living organisms, where does phosphorus show up? And phosphorus is, phosphates. No, but it doesn't have to be DNA, does it? It could be ATP. So think of biological compounds. Certainly DNA, RNA has phosphorus in it. ATP, the energy storage molecule has phosphorus. There's a lot of phosphates around. So I take that back about exclusively DNA. So we're going to take some of this radioactive phosphorus, we're going to inject it into some bacteria, and then we're going to monitor the bacteria and see where the phosphorus ends up. At some point we'll probably do some kind of we'll probably try to isolate different compounds from the bacteria and determine what are the metabolic pathways that the phosphorus goes through. So maybe we just put it in as phosphate with radioactive phosphorus and see how the bacteria makes use of that phosphate that we put in. It says after 1 hour the cells are going to be washed. 70% efficient detector is going to pick up these beta decays that are taking place. They want to find out how much of the phosphorus was taken up. So I guess what's happening here is we do just put probably phosphate in, and or phosphorus, and then we wash off the bacteria, and so everything gets washed away except whatever phosphorus has already been taken up by the bacteria and incorporated into some kind of a molecule that's held within the bacteria. Now the half-life, I looked this up in Appendix F, which is my friend, and it says the half-life of the phosphorus 32 is 14.27 days. And I took this Curie stuff, and I immediately converted it into something that makes sense to me. And so this 0.016 microcurie times the definition of Curie said that the sample is currently decaying at a rate of 592 decays per second, and that just makes a lot more sense to me. That's a lot more intuitive. So I got an R naught of 592. Now it says, what's going to happen after 1 hour? Well, if it starts out decaying at 592 and it's got a half-life of 14 days, will I even notice a difference after 1 hour? So I just did a quick check, and it says the rate of decay of 592 after an hour has dropped to 591, and I'm thinking, okay, 1 hour is insignificant compared with the 14.27 days of the half-life. All right, now I took the half-life and I calculated lifetimes because my personal choice, I like working in terms of half-lives, of lifetimes. And it says that the lifetime in days is 20.6, but the lifetime in seconds, and I'm going to end up needing both, is 1.78 times 10 to the 6th. Oh, and I also converted it into hours. So I've got the lifetime in whatever units I'm going to need it in to carry out the calculations. Now, what was the size of the original sample? So the original sample, I can count the number of phosphoruses. That would be R0 times the lifetime. And that worked out to be just over 1 billion. So I didn't start out with such a large number. It was only about 1 billion radioactive nuclei. That was the size of the sample. Now, the mass of 1 billion phosphorus 32s, so I'm going to use 32.0 grams per mole. That's my molar mass. And that says that the amount of phosphorus 32 in the entire that we placed in the bacteria is 56 femtograms, 10 to the minus 15. So you can imagine these are tiny, 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 really tiny samples. These are not going to be measured out on a scale. We're going to have to start with measuring the R's and determining the masses from those. So 56 femtograms, that's imperceptible. So let's see, what happens? It says in the sample, after in the sample, let me check the numbers here. I'm trying to see what comparison we're making here. It says that in the sample, oh, it's a 70% efficient detector. Oh, it records 720 counts per minute. There we go. So what's happened is, of course, so this is the R value that we measure. I should have gotten another R in here. So the R of the sample, once we've washed away the phosphorus which has not been taken up by the bacteria, then the remaining phosphorus counts out at 720 per minute, which is 12 decays per second. Now, I don't think I ever got my 70% in there. Uh-oh, that's going to throw it off. I didn't get the 70% efficiency. Okay, so I had to scale up the actual decay rates. All right, so this is off by 70%. So 12 decays compared with the 591, which is what we were expecting. The full sample of phosphorus would have been decaying at 591, puts us at about 2%. Now, I didn't divide through by 70%. So that needs to get divided by 0.7, and that's going to boost us to about 3%. So it should come out to be just about 3% of the phosphorus has been taken up by the bacteria, is my prediction. Okay. Questions on that? Okay, now exposure to radiation, the standard unit to represent exposure is called 1 gray, G-R-A-Y, and it goes by the abbreviation big G, little y. 1 gray is 1 joule of ionizing radiation per kilogram of the sample. So let's say, this person is exposed to some radiation source as well as some other material that was in the room. Everybody here has been exposed, all the materials. The dose that these samples have received is equal to the energy of the radiation divided by the mass. And here are the units we're going to measure this in. Now let's do this. Let's take a sample of water and let's expose it to some X-rays. So let's say that you're working in a medical lab and the coffee machine is broken, it won't heat the water, and you go, well, there's an X-ray machine down the hall. I could just take my mug down there and put it in the X-ray and turn on the X-rays, and I could heat up my water that way. Is that a good idea? So, so here are these photons that we're generating in the X-ray machine. And let's say that you turn on the X-ray machine and you give the water a dose of 10 gray. Now for biological systems, for humans, 10 gray is considered to be a lethal dose. Now there's a specific reason for that, and that's because of our bone marrow. So the blood cells are continually being replenished by a bunch of stem cells in the bone marrow, and cells that are always in the process of dividing are very susceptible to radiation. So radiation it has the biggest impact on cells that are currently dividing. A lot of times cells that are in the process of dividing that are exposed to radiation will just shut down. And so the 10 gray is lethal because it will shut down all of your stem cells in your marrow. And so it's not immediately lethal, but you stop producing blood cells. Now you can actually use this as a medical procedure, a medical technique. When we do stem cell transplants, patients that may have cancer, for example, what we can do is we can use high radiation to destroy the cancer. But what that does at the same time is it takes out the bone marrow. But what you can do is you can have either the patient stores some of their bone marrow in advance. So a patient can store bone marrow in advance and then be exposed to what would otherwise be a lethal dose of radiation. And then you can bring the stem cells back and put them back in the patient, and the patient survives. Or you could have a donor. You could have someone who is a donor. You could give the patient very high levels of X-ray therapy, and high enough that their own stem cells are shut down, but you could then replace that with someone else's stem cells, if there's a match. So, so in any case, let's get back to our heating up our coffee, or the water. So the water right now is at 20 Celsius, and I'm thinking I want to get it up to, I don't know, 40, 50 Celsius, 60 Celsius. Not that hot, right? Anyway, I got to think about what temperature the coffee should be. Let's see what happens if we give it 10 gray. Now, 10 gray would be 10 joules for every kilogram of water in that sample. So what I can do is I can go back to chapter 19, probably. So back in chapter 19, we introduced specific heats. So this Q is not the Q we've been looking at for nuclear reactions. This is the Q from thermodynamics. And so what we can do is say that the temperature increase, the question here is 10 gray enough to raise the water up to a nice, warm, toasty temperature of, I'm guessing it's probably, we don't want 60, right? 40? 40 Celsius? 40? I've got to look that up. I promise I will look up how hot is, what's the temperature of hot water that we drink. So I can solve for delta T. I can put in the 10 gray by putting in 10 joules per 1 kilogram of water. And then I can put in the specific heat for water. And the specific heat for water is 4,186 joules per kilogram per Kelvin. And that's enough. That's the units get taken care of. So that 10 gray actually substitute into the Q and the mass. That's a twofer. And when I calculate the delta T, it's very disappointing. So if I give my water a lethal dose of X-rays, it raises the temperature by 0.00239 Kelvin. That's it? So, sometimes when I was a kid, I remember, a friend would break their leg or something, someone would go to the emergency room, and we would talk about getting x-rays, and we would say, so when they did the x-rays, could you feel the x-rays? Oh yeah, I could feel the x-rays. Could you feel the x-rays? Yeah. It felt really warm when the x-ray machine was turned on. Boy, I hope not. So how could such a tiny, tiny amount of energy be lethal? And that's because the x-rays are packaged into photons, where individual photons have an enormous amount of energy. Almost all of that energy goes into breaking chemical bonds. So this is not very much energy. You know, I bring in a liter of water, and I heat it up with 10 joules, and that's how much the temperature goes up. But if I expose it to 10 joules of x-rays, that would be a lethal dose for a person. Okay. Anyway, it's surprising just how much injury can be done by a small amount of energy of x-rays. Okay, and this chart here is reminding us that not all high energy particles are the same. Energy for energy, this is called a quality factor, which I all think is kind of hilarious, although maybe it's not. The quality factor is that when I'm thinking in terms of dosage, photons, x-rays and gammas, they get multiplied by a factor of 1 in terms of the risk that they pose. Electrons, too, are a factor of 1. Fast protons. Neutrons are higher, so MeV for MeV, neutrons produce more damage. Fast neutrons can be up to 10, and alpha particles can be up to 20. Okay, so you can get more damage based on what type of particle you're being exposed to. All right, that is it. So we did we heated up our coffee using the X-ray machine. This is interesting stuff at the end of the chapter, and then earlier on too, looking at some of the fusion. Well, maybe this is a good slide to end on, since this is just around the corner, right? A reliable nuclear fusion power plant. So whatever questions you guys have, let me know. Stop by office hours. Stop by and we will get those questions looked at. I hope these 2 chapters on nuclear physics have been interesting and informative. Again, what I always feel like is we're able to fill in some of the gaps that get left maybe in chemistry or in biology classes, and fill in some more of the details, and introduce some surprising results. Okay, hope to see you guys in office hours. Bring your questions in.